Today we're going to look at mechanisms. There are 6 different types of simple machines, and today we'll look at a lever, a wheel and axle, and a pulley. Simple machines are mechanisms that manipulate the magnitude of force and distance. Magnitude of force is how much. How much force are we putting into it? And distance is how far are we taking that force? How long are we taking that object? So we're going to look at 2 things, magnitude of force and distance. We're going to look at lever, wheel and axle, and pulley. You can see from the picture in the center that wheel and axle are considered one simple machine. Three more simple machines are the inclined plane, like the roller coaster you see there going up, a wedge, like that axe, or a screw, which you see here on that lift for your car. Mechanical advantage, or MA, is something that we can't see, but we can measure it. We can measure what happens when we use our simple machines. We measure it as a ratio. It's measured as a ratio of the magnitude of the resistance and effort forces. That means the magnitude, how much resistance, how much weight is going on, how much effort is required to move that weight. We can also measure it in distance. How far is it traveling? We look at the ratio of distance traveled by the effort and the resistance force. The resistance is usually the weight of an object that has to be moved, and the effort is how much you need to put into it to make it go. So we can either look at the magnitude of it or the distance it's going. Calculated ratios allow designers to manipulate speed, distance, force, and their function. Be sure to view this presentation or this PowerPoint in presentation mode so that you can see the animations working. On this slide, we'll look at an example of mechanical advantage. On this inclined plane, we'll see a mechanical advantage of 4 to 1. That's the ratio. What does it tell us about a mechanism? Well, we can look at a magnitude of force. In this case, the effort force magnitude is 4 times less than the magnitude of the resistance force. So we'll have to let that settle in for a minute. But it means that it takes you 4 times less work to push those boxes than it does for it how heavy it is. We can also look at distance traveled by the force. The effort force travels 4 times greater distance than the resistance force. So if you look at the yellow box, it's going 4 times as far as that box on the left, the orangey type box. In this example, we're looking at how to calculate the work. So work is the force applied on an object times the distance of the object as it travels parallel to the force. It needs to be parallel in order to do this. Please make sure you're in presentation mode to see the box move. So if you push this object along the line here, it's parallel distance to the force. They're going in the same direction, they're lined up. So work equals force times distance, and those 2 little lines on the bottom mean parallel. So this is where it gets a little tricky, but it's also really awesome. Looking at work on this inclined plane, you're going to see that the product of the effort times the distance traveled will be the same, regardless of the system mechanical advantage. Remember that this yellow box goes 4 times further along in distance than the orange box did, but it was easier to push. The orange box was more difficult to push, and doesn't go as far. So their work would be the same, but the mechanical advantage is different. This slide has a lot of information. What do you need to know? 1 is the magic number. If the mechanical advantage is greater than 1, then it takes less effort to overcome the resistance. If it's less than 1, it takes more effort to overcome the force. So why would you want to use more effort? Have you been to the gym lately? When we look at an ideal calculation, it's theory-based. It's not happening actually or in real life. We're going to ignore friction. You know, when you slide that block up the inclined plane, friction's in there, but we're going to ignore that for now. The ratio of distance traveled by effort and resistance force is what we're looking at. So we use this calculation for efficiency and a safety factor design for calculations. We can determine whether something we might put together or use is safe. In this case, there's a formula. The ideal mechanical advantage, or IMA, is equal to the distance traveled by the effort force divided by the distance traveled by the resistance force. We'll take a bigger look at that later. When we look at actual mechanical advantage, or AMA, it's an inquiry-based calculation. We are going to look at frictional losses, and then we use it for efficiency calculations. How well does your simple machine work? So in this case, we look at the ratio of force magnitudes. Remember, for ideal, we looked at the ratio of effort magnitudes or distance magnitudes. Now we're going to look at force. So the actual mechanical advantage is equal to the resistance force, or its magnitude, divided by the effort force, its magnitude. Have you been able to think of a machine that has a mechanical advantage greater than 1? Windmills do this. With just a little breeze, we have proportionally less effort, force required to overcome the resistance. Those things. Have you been able to think